Okay, in this screencast, we're going to talk about an introduction to direct current electric circuits. And we just learned about how like charges repel each other and how unlike charges attract each other. We learned a formula to be able to calculate that force through Coulomb's law. And what we have in a circuit is you've got a power supply, in this case a battery. I've shown here with two lines. This is going to be the positive side, this is going to be the negative side of the battery. A battery has a positive terminal where there's an excess of positive charge built up, and then on the negative side there's an excess of negative charge built up. So the battery has all this stored energy, because when you separate charge, it's kind of like when you pick up a large rock and move it to the top of a giant hill with gravitational potential energy. You've got a lot of electrical potential energy stored in that battery, because you've got all these charges that want to be mixed together. The negatives want to run to the positives, but you've separated them in this battery, so you've got all this stored potential energy. And a battery does that chemically. So it takes its chemical potential energy and it splits up that charge. So what you've got in this basic circuit that I've drawn is you've got the battery, which is a power source. Again, the positive terminal of the battery is represented by the longer line, the negative terminal by the shorter line, and then the black lines are the wires, and these squiggly lines are resistors. Resistors are devices that you put in a circuit, like in your home. A resistor would be like the light bulbs, the TVs, the toasters, the things that you plug into the wall. Those act as resistors. They draw current, and they use the power that's supplied not by a battery in your house, but by the electric company. So in a DC circuit, unlike your house, which runs on alternating current, in a DC circuit, a battery supplies direct current, which always goes in the same direction. In your house, believe it or not, the current switches directions 60 times a second. That's 60 hertz alternating current. So in this direct current battery, we've got current flowing from the positive terminal to the negative terminal. Now that's a convention, because the only kind of charge that can move through conductors is a negative charge. So when you've got a metal conductor like a copper wire or a silver wire, the electrons are the things that actually move. So a battery is actually stripping the electrons from the positive ions and grouping all those electrons on the one side of the battery. But we show the positive charge moving to the negative terminal by convention, because Ben Franklin is the one who defined the electric circuit conventions, and he's the one that created or invented the positive and negative symbols for the two types of charge, and he thought the positive charge was the one that was moved. So all through the development of electricity, the positive charge was always thought to be the one that moves, and it was much later on that they discovered the electron's the thing that moves. But since convention had already been established, we show symbolically that the current goes in the direction from the positive terminal to the negative terminal. Current is the symbol for current is that capital I that I have there. The units are amperes or amps. The symbol is a capital A. Resistor has a symbol of capital R, and resistance is in ohms, and that can be shown with a symbol, an omega symbol. So a resistor is like a restriction in a pipe. So you can actually think about current in a wire like water in a pipe. The battery would be like the pump that's pumping the water through the pipe. The resistor, the wire is the pipe itself. The current is the water flow, the amount of flow through the pipe over time. And the resistor is like a constriction within the pipe. So it uses up some of the pressure from the pump. So by the time the water gets back to the pump, by the time the charge gets back to the battery's going to give it that boost again after it passes through the battery. So you can think of a pump and a pipe system you can use that as an analogy for a current in a direct current in a circuit. Now charge is conserved, so you can see the current in this case going from the positive to the negative terminal. It's moving in a clockwise fashion. Okay, so it's got nowhere else to go, so that same current is going to go all the way through the circuit and come back into the battery on the negative terminal. So just like water in a pipe, in order to keep pumping the water through the system, you have to have water coming into the pump, and the same amount of water comes in as goes out of the pump. So the same amount of charge, same number of electrons come through the wire on the negative terminal as go out of the wire on the positive terminal. So that's kind of how a basic electric circuit works. Those are the symbols that represent the different devices, batteries and resistors. I'm going to show you two different kinds of circuits. First, a series circuit, and then resistors that are in parallel. And we'll talk about how we analyze those different types of circuits. Staying on this slide for just a minute, actually, I can point out here that because my current that comes out of the battery right here, so this current coming out of the battery right here, has nowhere else to go, it's only got one branch to follow, that this is called a series circuit. And we say the resistors are in series. And that means that all the current that goes through one resistor goes through the next resistor and goes through the next resistor. So the current does not branch off into different branches of the circuit, which is something that you'll see when resistors are in parallel. There's different branches, and I'll show you that right now. Okay, so here we have our battery with our positive terminal and our negative terminal. We'll have a current going clockwise again, coming out of the positive terminal. We'll call this I1. And notice that when the current gets to that junction right there, it has a choice of which branch to go through, either R1 or R2. So some of that current is going to go in this direction. We'll call this I2, and some of it is going to go here, I3. So that current, once it branches off from that node, that junction point I should call it, it's all going to go through R1, and then it's going to come into this junction point right here. So all the I2 will come into that junction point, while I3 will pass through resistor 2, and then all of I3 will come back into this node right here. And so I2 and I3 will join together again, and you'll have I1 back after downstream, if you want to think about that, of that node, if you want to think of it that way. So I1 is made up of the sum of the amount of current in I2 and I3. Again, it might be useful to think of a pipe where the amount of water that flows into a fork in the pipe, you know, some of that water is going to go in one direction, some's going to go in the other direction, but it's all going to come back together again down here at this node at the bottom, and you'll have the same amount of water that you had going into the junction. So the same amount of current I1 will come into the negative terminal of the battery as goes out of the positive terminal. So this is called resistors that are in series. Resistors that are in parallel. And you can kind of understand why they call it parallel, because the two branches, we can draw them as if they are parallel to each other. But anytime when the current has a choice, and I use that word as if the current was choosing, but when the current has two paths, probably a better way to word that, more than one path, to take, those resistors are in parallel. So anytime the current is branching, you know, at a fork in the wire, we will say that the resistors are in parallel. So the reason that's important is we're going to try to analyze a circuit to try and figure out how much current is going through these different branches of the circuit, because it's important to know how much current is in a circuit. First of all, it's going to be on your AP exam, so you want to know that for doing well on the AP test. But the practical application of this in your house is you want to know how much current is going to go through different circuits in your house. So you want to know how to size the wire. So the size of the wire is dependent upon how much current is going to go through the wire. The circuit breaker is designed to trip at a certain current through the circuit. So if you have too much current going through the circuit, which would cause that wire to heat up and maybe cause a fire, before that happens, a circuit breaker is designed and sized appropriately for the amount of current in the circuit to protect that wire, and it will trip and break the circuit. Basically, it's like opening a switch so that there is not a closed loop anymore and the current won't flow through the circuit anymore. Obviously, you have to have a closed loop in the circuit for the current to flow, for the charge to come back in the negative terminal of the battery to keep flowing through the circuit. If you broke this circuit anywhere, so if you just cut this wire right here, now you don't have any flow anywhere in the system because you don't have a closed loop. That's what a circuit breaker does. So that's why we want to size this, wire. We want to know how much current is going through each individual branch. So I'm going to teach you how to determine that in the next couple slides. Okay, so here's another basic circuit, and I've actually put some numbers in now. Batteries, the amount of energy in a battery can be represented by the amount of voltage in the battery. Now, voltage isn't exactly energy, it's actually energy per unit of charge. We're not going to necessarily worry about that. The more voltage a battery has, the more potential it has to split the charge up. So in your calculators, you might have 1.5 volt batteries. You know, they're always putting out 1.5 volts for each battery, and there's probably 4 of them. Excuse me. That means your battery or your calculator uses about 6 volts of, it's got 6 volts of power supply to the circuits in the battery. So in my circuit right here, I'm showing a 9-volt battery. So the units of in the battery are volts, and that's represented by a capital V. And Ohm's law I've written up here, voltage equals current times resistance. Okay, so this is true. This is not a law of nature. This is for devices like resistors that are ohmic. And what that means is they follow Ohm's law. That's a linear relationship. So devices that are ohmic, as I increase the voltage, in other words, if I go from 3 volts to 6 volts to 9 volts, keeping the resistance constant, my current should go up proportionally. They're directly proportional to each other. Not all devices are ohmic. Light bulbs tend to not be ohmic because they heat up, and so the resistance is not constant. So as you heat up devices that are ohmic, voltage versus current looks like this, the slope being the resistance, but it turns out that light bulbs tend to do this. So as the voltage goes up, actually I think I got that wrong, sorry about that. As the voltage goes up, now I can't erase that. It goes the other way, sorry about that. As the voltage goes up, less current goes through it. So the resistance tends to increase as time goes by because of the heating up. Conceptually, that might be important for the AP exam, but mathematically, all the devices that I'm going to show you, all the resistors, we're going to assume the resistance is constant regardless of the current. So we're going to assume that all the resistors are ohmic in the lesson that I'm about to teach you. So we'd like to figure out how much current is coming through the wires here so we can design our circuit. In order to do that, you need to understand that across each one of these resistors, there's a little bit of a voltage drop. Okay, and voltage drop, I mean some of that 9 volts is used up in this resistor. Some of that 9 volts, I'll call it V2, is used up there, and some of that 9 volts is used up in here. Well, the sum of those three, the amount of voltage used up in first resistor and the second resistor and the third resistor, is going to add up to the 9 volts that I have available. Well, using Ohm's law, I know the amount of voltage that's used up in the first resistor is whatever the current is times resistor 1 plus whatever the current is times resistor 2 plus whatever the current is times resistor 3. That will add up to my 9 volts. And remember, the current is the same through all 3 of these resistors because that same I is going through this system. It doesn't have anywhere to branch off. These resistors are in series. It's a pretty easy circuit to analyze. So since I is the same, I can factor I out, and I would just have I times R1, R2, and R3 equaling 9 volts. So I know easily how to add up those three resistors, but it's interesting we have a name for these. It's the equivalent resistance. It should be an EQ down there, REQ, and that just equals R1 plus R2 plus R3. So the equivalent resistance of this circuit, I'm going to see if I can move that, give myself more room. Didn't want to cooperate, so it stays down there. So the R equivalent here is just going to be equal to 2 plus 3 plus 4 equals 9 ohms. So the equivalent resistance of this circuit is as if instead of a 2, 3, and a 4 ohm separate resistors, it's as if there was one 9 ohm resistor. So the amount of current in that circuit is the same with those three resistors as if there was a single 9 ohm resistor. Let me show what it would look like. That would look like a circuit like this. So the amount of current in our circuit is the same as if there was one 9 ohm resistor right there. So since V equals I times R, it's pretty easy to figure out that the amount of current is equal to V over R, which is the 9 volts divided by the 9 ohms, which would be 1 amp. A being the amp, okay? So there's 1 amp of current going through our circuit. So I know now how to size the wire. When you go to Home Depot, you can actually buy different gauge wires that's different thickness based on its usage and how many amps of current you're going to have running through it. And you can now also size a circuit breaker based on how much current that wire is designed to carry. So that's a simple series circuit. That's pretty straightforward. Now we're going to talk about how to analyze a circuit where the resistors are in parallel, and we'll go through that. Okay, here's a basic circuit. I'm going to have a 9-volt battery again, and there's a positive terminal and a negative terminal, so the charge is going to want to move, the current is going to want to move in this direction. I'm going to call this I1. It gets to this junction point here, and it's going to split off, and I'll call this I2, and I'll call this I3 in that direction. And of course, these two are going to come back together here. I3 on this side, I2 on this side, come back together at this junction, and they'll come back to I1 right there. So in this circuit, I1 is equal to I2 plus I3, as we've seen before. So how do we analyze this circuit? How do we figure out how much current is in those different branches? Well, what we have to do is find the equivalent resistance as if these the 2 ohm and 3 ohm resistors were replaced with a single resistor, and then we'll be able to figure out what I1 is by finding what the equivalent resistance is if we were to combine the 2 and the 3 ohm resistor. It's not as easy here to just add the 2 and 3 ohm resistor. We have to do a little bit of thought, have a little bit of thought here. So this 9-volt battery, it's as if, it's kind of like establishing a reference point for gravitational potential energy, but this is electrical potential energy. So we're going to pretend this negative side of the battery is at 0 volts, and the positive side of the battery is at 9 volts, okay? I don't know if I can erase that, sure enough, okay. So since there's no resistors between this point on the positive terminal of my battery right here and my junction right here, there's no loss of energy, there's no drop in voltage. So if the positive terminal of the battery is at 9 volts, then this junction is at 9 volts. Likewise, on the bottom side of this battery, if the negative terminal is at 0 volts, so that the change in voltage across the battery is 9 volts, and there's no resistors in this part of the wire all along this bottom edge here, that means that there's no voltage loss across that wire. We assume ideal wires. And this junction point here would be at 0 volts, as would this be at 0 volts. So this would also be at 9 volts. And the reason I can say that is there's nothing along the length of this wire. I'm tracing across the top of the wire right now. There's no resistors that cause any loss of energy. I assume my wires are perfect. They aren't really, but it's kind of like assuming a frictionless surface, so that whatever amount of energy I had on the positive terminal there, I've got the same amount of energy at those top two nodes. So that's going to be useful in our analysis here, okay? Because the voltage drop across each one of these resistors, well, let's talk about the current in each one of those resistors. Actually, I'm going to start with an equation that if we were able to combine that 2 and that 3 ohm resistor into one equivalent resistance, then the voltage for the whole circuit, my 9 volts, would be equal to current 1 times the equivalent resistance. Okay, so this would be my 9 volts right here. The equivalent resistance would be whatever the 2 ohm and 3 ohm resistor would be if I could boil them down into just one resistor. So to find out what this equivalent resistance is, we're going to start with this equation right here. And we know that I1 is equal to I2 plus I3, but I2 is just equal to the voltage across resistor 2 divided by how big resistor 2 is. I3, likewise, is equal to the voltage across resistor 3 divided by the size of resistor 3. So solving this equation for I1 down here, I1 is equal to the whole voltage for the whole circuit divided by the equivalent resistance. So substituting all of those into that top equation right here, so substituting all of those into this equation here is going to give me an equation that looks like this. The V for the whole circuit divided by the equivalent resistance equals the V across resistor 2 divided by the size of resistor 2 plus the voltage drop across resistor 3 divided by resistor 3. But we've already said that the amount of voltage across resistor 3 and resistor 2 both, we're going from 9 volts down to 0 volts across both of those resistors. So delta V2 is 9 volts, delta V3 is 9 volts, and the voltage for the whole circuit is 9 volts. So I can divide both sides by 9 volts, and I just get 1 over Req equals 1 over R2 plus 1 over R3. And that's an equation I can use to solve my equivalent resistance and find out what I1 would be. So I1 is going to be 1/2 plus 1/3, which is, let's see, that's 3/6 plus 2/6, that's 5/6 of an ohm. Actually not an ohm, because that's not the answer. That's the reciprocal. Remember, that's the reciprocal of the equivalent resistance. A common mistake is to forget to flip your answer when you're calculating the equivalent resistance in a parallel circuit. So don't forget to flip this upside down so that the equivalent resistance of this circuit is 6/5, which is 1.2 ohms. Interesting that that equivalent resistance is less than either resistor individually, and that is a characteristic of parallel resistors. So let's go to the next slide. I'm going to give you 2 general equations to calculate equivalent resistance in the different kinds of circuits. Actually, I was getting ahead of myself. We need to finish our circuit analysis here on our parallel resistors. So I just figured out that our equivalent resistance, let me first label this I1, I2, and I3. We just discovered that our equivalent resistance in this circuit was a 1.2 ohm resistor. So that's as if this circuit had a single resistor. If I could combine those 2 resistors, the 2 and the 3 ohm resistor, it's like having one 1.2 ohm resistor. So the current in this circuit, if that was my circuit, would be V divided by R, which is the 9 volts, divided by the 1.2 ohms, which works out to be 7.5 amps. Okay, so that tells me that I1 is 7.5 amps, because I1 is the same as this current coming out of the 9 volt battery up in my circuit where I combined the 2 resistors. all of the current coming out of the 9-volt battery is going to split between I2 and I3 in the actual circuit, but it all comes back together again at this bottom node here, and so this is my same 7.5 amps down here. So now how do we figure out what I2 and I3 are to size our wires in those two branches? Well, we already know that this is, we already know that we've got 9 volts across here. So this is 9 volts here, this is 0, this is 9 volts here, this is 0 there. So for I2, that's just delta V2 over R2, and that is 9 volts divided by 2 ohms, which is 4.5 amps. I3 is delta V3 over R3, the voltage drop across R3, which is 9 volts, this time over 3 ohms. So not surprisingly, the larger resistor, the 3 ohm resistor right here, has less current going through it, 3 amps. The smaller resistor, which is 2 amps, over on this side, I2 is 4.5 amps. So it's like the bigger constriction, the 3 ohm resistor, is like a smaller pipe. Less water is going to flow through that pipe. The 2 ohm resistor is a little bit bigger pipe. It's a constriction, but it's bigger than the 3 ohm constriction. So more current, more water is going to flow through that one. Just as we expected, those two will add up to the 7.5 amps that I've got running through the main part of the circuit that goes through the battery. So a general equation for the two different types of resistance, the two different types of resistors, the ones that are in series and the ones that are in parallel, I'll give you on the next slide. Okay, for resistors in series, the general equation that we applied, that we derived actually from the simple circuit I showed you in the first couple slides, is just a simple addition of all of the individual resistors, and that will give you the equivalent resistance for a series of resistors that are, for a couple of resistors or multiple resistors that are in series. Resistors that are in parallel, where the current has a choice of which branch to go through, the inverse of the equivalent resistance is equal to the inverse of each individual resistance added together. So don't forget at the end of the problem, when you're finding the equivalent resistance of parallel circuits, remember that on this side of the equation, what you're finding over here, when you do all these 1 over R1, 1 over R2, you're finding the inverse of the equivalent resistance. So you have to, the last step of those problems after you add all these up, is you have to find the inverse of your answer. Like when I took the 5/6 and I flipped it and made it 6/5. Okay, so what I'll do in the next screencast is I will show you how to simplify and analyze a circuit that's got both series and parallel resistors in it, and we'll go through a couple example problems.